the lower bound theory, we call it. See, this is something slightly different from the usual sorting kind of thing. Okay, the other one is called as bucket sort. So this one, like, the lower bound theory, as I said, it is slightly a different kind of a discussion here. And then we will move on to a very peculiar kind of sorting, because we are not going to compare in this bucket sort. Unlike the earlier sorting methods, like your merge sort, quick sort, insertion sort, heap sort, anything. See, these are the sorting algorithms which predominantly follow the strategy called comparison based. Okay. But bucket sort is not going to follow that. And what is this lower bound theory on sorting? Now, the meaning of the lower bound is coming from the fact that if you take insertion sort, now the the worst case time complexity is n square, right? And if you take merge sort, heap sort, quick sort, etc., average and the best case is n log n, right? So I'm talking about the sorting algorithms that we have already discussed. So if you see the worst case performance of some of these sorting algorithms like bubble sort, insertion sort, it comes to n square. Then if you take the other sorting algorithms, the lowest one is n log n, right? N log to the base 2, that is obvious. N log n. N log n is better than n square. In other words, n log n is less than n square. So, I mean, any sorting algorithm may not take beyond n square. And we can also prove that we cannot get a sorting algorithm whose time complexity is less than n log n. Okay. Except, I'm talking about, again, comparison based. So don't take up the argument of that there are some sorting algorithms where we could do it better. Some exceptions are there, but comparison based sorting, even of course bubble sort, best case is there of the order of n, but that again with a flag, all that. So I'm talking about in the worst case with the comparison based. So in the worst case, we can prove that n log n is the maximum, best time complexity which you can get in the worst case. What I mean to say is that I cannot reduce this below this n log n. How does it help us? It helps us in the argument that there is no need to, go on searching for or designing algorithm, looking for the design of the algorithms where can I reduce this time? Now, there is no need to do that because you cannot do it. But how do I say that? What is the proof? So that's exactly what we are going to see in lower bound. So we are going to prove that in comparison based, you cannot make it better than n log n. You minimum require n log n time in order to make sure that your sorting works. Okay. Then we will go for bucket sort, in which we will not use the comparison based strategy, as I've already mentioned. So the strategy here is slightly different, right? But there are some disadvantages. The advantages, of course, in terms of the time complexity, but we also have some disadvantages. So that's going to be the today's discussion. Okay. Right. So now, to give you further insight to what I have just now said, merge sort and heap sort run in the worst case or n log n time, and quick sort runs expected is n log n. Worst case is n square as far as the quick sort is concerned. Forget about that. But in an average or the worst case, most of these algorithms, except quick sort, require n log n time. One wonders if there is something special about this. That means no sorting algorithm can do better than this. That's what I said. You can prove that comparison-based sorting algorithms cannot do better than this. So we can prove that any comparison-based sorting algorithm runs at least this much of time. So comparison-based means algorithm makes all its decisions based on how the elements of the input array compare to each other. For example, bubble sort, adjacent elements are compared. If you take quick sort, you take the pivot and then compare with the rest of the elements and so on. So you take any algorithm, especially these kinds of comparison based, the elements are compared at least, n minus one element, insertion sort also. But we have to prove now, that's our task. We have to prove that we require at least n log n time. See, if that can be proved, then we don't need to spend time in doing research of looking for some sorting algorithm, comparison based, where I can go for little less than what we are talking about here in log n. So in order to do this, we are going to use what is known as decision trees. Okay. So given an unsorted array, the algorithm must decide how to permute the array. Say, observe carefully, because this may be a little confusing. Okay. Because we are building the theory background for proof of this minimum n log n. So if at all you want to follow this, what do you call, comparison based, in order to get the sorted output, you have to actually compare in all possible manner. That means all permutations and combinations. So we say that there are n factorial possible, ordering that requires on n elements, and a comparison based algorithm may be asked to do this n factorial combination. So I think you will understand by looking at the figure and also by picking some value, specific value for n. Okay, so we will consider three elements, that is n equal to 3. So we can just say that we need 3 factorial. That means 6 combinations we require in order to make decisions and make sure that you will be able to sort it, because we are trying to provide a generalized theory or the proof here. When I say n equals 3, the values of n could be in any order. I may have sorted 5, 10, 15, or I may have 10, 5, 15, or I may have 5, 10, 15. I mean, any combinations of these three numbers. So how many such combinations we can have? Only 3 factorial. This is nothing but simple mathematics, all permutations and combinations. That's all. Okay, so the decision must be based on comparison, in which each provide one bit of information. So I'll consider this as yes or no, or 1, 0. Anything is okay. Because when I compare two elements, either, for example, when I say 5 and 10, 5 maybe are okay, A1 and A2. Let's take A1 and A2, or B1 and B2, because I've already written that. So B1 and B2. There are two numbers given, two elements. So B1 may be greater than B2 or B1 less than B2. That's the possibilities. which means it's A either yes or no. So when I say B1 greater than B2, depending upon the values of B1 and B2, it can be true or false or 1 or 0. So one bit is enough. So to accommodate n factorial possible outcomes, we need at least log of. Why this log is coming, that I'll show you in the decision tree. Because by going through this decision tree, it is possible to, permute all these n values in such a way that it is formulated as a tree structure where the height of the tree is log n for n elements. But here we have n factorial combinations. So the number of leaf nodes will be n factorial. So that's why the height will be log n factorial. So let's now see this example, as I said earlier, slide. Let's consider three, numbers A1, A2, A3. It could be anything, but we have to take it more general. That's all. If this is proved, then we can extend for any value of n. So I'll just take this as yes and this side as no. OK. Similarly, this side 1, which means yes, and 0. Similarly, this side, the next level, so this is 1, this is 0, 1, 0, 1, 0. Okay. Now we'll just start with the root. For the given value of A1, A2, A3, if A1 is less than A2, assume that it's true, then if we compare the other two elements A2 and A3, and if this also is true, we know that A1 is less than A2 and also less than A3 because already A2 is less than A3. So A1 is the least among these three. And since this is true, A2 should be less than A3. So A2 has to come after A1. A3 is the last one, biggest, because if this is true, A3 should be the largest. So what is the ordering? 1, 2, 3. That is A1, A2, A3. So this is what I call it as one possible combination. Similarly, you can see here 1, 2, 3, 4, 5, 6. So when n equals 3, we have n factorial, which is 6, right? 6 combinations. N factorial is nothing but 6 combinations. That's very simple, A1, A2, A3, A1, A3, A2, A2, A1, A3. So like that, that's what I'm going to show you with the leaf nodes. Okay, so eventually you will get all the combinations appearing as leaf nodes because that's the decision taken. Because after comparing this, you are able to take a decision that what are the orderings of these values. Okay, right. Okay, this is over. We have already proved this. Now let's take the other path. A1 is less than A2, but this condition is false. What does it mean? That A2 is no longer, A1 is less than A2, but A2 is not less than A3, which means A3 is less. And if A1 is less than A3, A1 has to be first, obviously, but A3 will come next because it is false, A2 and A3. A2 is not less than A3, but actually A3 is less. So A3 will come as second. And since this is false, A2 is greater and, compared to 3 also. Because we are comparing again with A1 and A3. So 1, 2, 3. With 3 comparisons, you are able to find out which one is the least. For example, this condition says A1 with respect to A2, And this condition says that it is also less than A3 because this is true. So A1 is less than A2 and also less than A3, which means A1 has to be the first one. Now the competition is between 3 and 2, that is A3 and A2. So that is very easy because we have two comparisons here. A3 is greater than A2. Sorry. Yeah, A2 is not less than A3, but this is true because A1 is less. That means A3 is greater than A1, but not A2, which means A3 comes next and A2 comes third one. So this is another combination which we can generate. So similarly, this side, if you see that A1 is no longer less, so A1 is not going to occupy the first position. Whereas A2, there is a possibility. If A2 is greater and between A1 and A3, anyway, A1 is less compared to A3. Obviously, these two will come as the second and A2 will be the first. So this is also correct. So like this, we can, argue and conclude that the leaf nodes provide you the ordering, the ascending ordering of these three values. Okay, since I mean, irrespective of the value of n, we can actually, because it's a comparison based sorting. So we have, if we go through this tree or build this decision tree, ultimately you'll be able to sort. It all depends upon the elemental values. So that's all the difference. So now we have to prove that for any given value of n, so what is the time complexity of this, right? So if we can derive an equation and prove that its time complexity is n log n, that means irrespective of the value of n and any algorithm you select, comparison means you should spend at least n log n times. So that is what we call it as the lower bound theory. Lower bound theory simply means that for any given algorithm, what is the minimum time required so that below that there is no other possible. You have to prove it. For some algorithms, you will not be able to prove. For example, linear search, it is of the order of n, right? But we cannot say that, sorry, not n log n, it is of the order of n, linear search. See, we didn't keep quiet. We said that this is not the lower bound, right? So we have introduced another algorithm called as binary search, for which the time complexity worst case is log n. Log n is lesser than n, which means that this is not the lower bound. Now, can I do better than this log n? Okay, if something like of the order of 1, it's possible using hashing. So in the worst case is of the order of n, the lower bound is not n because we have binary search which can do better than this, lower than this. And we also can do with some constraints better than this, which is 1, nothing less than. So lower bound for this is of the order of 1. So the problem is that, getting the lower bound for some algorithms is not so easy. So that's what we call it as the lower bound theory. So in order for comparison sort to be correct, leaves of the decision tree must contain all possible combinations. 3 elements, 6 combinations. And any possible order. So there are n factorial permutations of the input array. So the decision tree must have at least n factorial leaves. Therefore, the height of the decision tree is log. I think we have already mentioned this. But now we have to derive an equation, right? That's the proof. This is the proof which we show in terms of the theorem. Okay, so what does it say? Any decision tree sorting n elements has height. This is a lower bound, omega. So n log n. So how do we prove this? So the proof is given here. Assume elements are the distinct numbers 1 through n. any numbers. So just for analysis purpose, say 1 to 100. So 100 elements are given in any unsorted array, unsorted way. So you have to sort it. So all combinations, if you put it, you'll get a big tree. So there must be n factorial leaves. I think we have already said n equal to 3, you get 6 leaves. One for each of the n factorial permutations or combinations. So tree of height h has at most 2 power h leaves because it goes in a binary fashion. Yes or no, yes, no, yes, no. So it's a binary tree actually. Not a complete binary tree, but it's a binary tree. So the longest path will give you the height of the tree. So this is also for any given h, 2 power h nodes will be there. So this should be greater than n factor or equal to, because that's the highest, or it would be less also depending upon the values. So which means that you can just take log on either side, log to the base 2, so h will come. So here log n factorial. So that's what we have written. So h is greater than or equal to log n factorial. Correct? Now I can just write n factorial as n into n minus 1. I think this is high school mathematics. Now we can apply log to individual terms. Okay, logarithm is plus. Actual multiplication will become plus with basic log functions. So when you do this, this becomes summation and so on. So when you come here, you can see that n by 2, when n is large, by 2 is n itself. Similarly here. So this becomes actually n log n. So that's the proof which we have for the lower bound time complexity for your any sorting comparison, any comparison based sorting algorithm. So you cannot get time complexity lower than n log n if you are applying your strategy as comparison based. So that is the proof. Okay, so any doubts? Okay, I think it's time up. So now we shall move on to the bucket sort. Recording, I think, should be happening. Yes, it's going on. Right. So the second part of our discussion today is on bucket sort. Now let's see what exactly the bucket sort means. It's also called as bin sort. And yeah, you can see here it's a bin sort. Sorting algorithm that works by partitioning an array into finite number of buckets. Sometimes we may call this as bins also. So there are a few variations of this. So let's first look into the easiest way of explaining this bucket sort. So what exactly this bucket means? A bucket means that it is uh, you know a sort of bin which actually holds the elements. Okay, and buckets. How many buckets we should have? Finite number it says, but essentially how to find out that how many buckets we require. So we have given elements, n elements, and we also have set of buckets. So these two are different. Okay. Okay. So each bucket, once you put the elements into these buckets, assume that we have so many B buckets. So the elements are going to be put in these buckets, and each bucket is then sorted individually, right? Either using a different sorting algorithm, because each bucket may have multiple elements. Now we need the sorted one in each, or by recursively applying. So this is where two different types or of bucket sort comes into picture. Either you allow only one element in each bucket, or you allow say m number of elements in each bucket. So there can be some limitation on this m. So you can't allow more than 10 elements in each bucket, let's say something like that. So if you are allowing more than one element in each bucket, then each bucket has to be sorted. Because the number of elements in each bucket is limited, so the sorting time is almost negligible. Okay, right. So the idea behind bucket sort is that if we know the range of our elements to be sorted, we can set up buckets. So this setting up of the buckets is again dependent on the maximum value which is there in this given n element. Supposing 100 is the maximum, then we need 100 buckets. Okay, we'll see how to reduce this later. And pick each element. So 100 is the maximum. Depending upon the elemental value, that element will be put into the appropriate bucket. So we'll just toss those elements into the buckets. I'll just explain with the example in the next slide. Then empty the buckets in order. That means you actually collate all these buckets so that automatically you will get the sorted elements. So here we don't compare anything. We don't compare element to element. Adjacent elements or first to last or pivot, nothing is there. No comparison at all. It is simply that you pick some element and put it in a bucket. Pick element, second element, put it in the bucket. That's all. I think this is very simple. Supposing assume that you have currencies in your pocket or wallet. Okay. Now, for example, you may have 10 rupee note, you may have 20 rupee note, you may have 50 rupee note, you may have 100 rupee note, you may have 200 rupee note, then you may have 500 rupee note, then you may have, no, that's the maximum. Okay, 1000 is gone, 2000 is gone. Okay, so now haphazard way, it may be there in your wallet. Few 100 rupee notes, few 50, few 200, no 500, let's say. Okay, so when I want to order them, I can just use 1, 2, 3, 4, 5, 6. 6 buckets I can have. One for 10 rupee notes, another for 20 rupee notes, another for 50. Likewise. So 6 buckets I will have. Whenever I pick a 10 rupee note, I just put it in the appropriate bucket. If I get 200 rupee note, doesn't matter. Any order it can come. First 10, next 200. 200 rupee bucket, I know. I just put it. Then what I do? I just collect all these things. So it is going to be in the order 10, 20, 50, 100, 200, 500. That's all. So that's exactly what we are going to do with an example and explain this bucket sort. So let us assume that we are given 10 elements. Okay. And the maximum value in this array is 15. So this is one drawback where we should first find out. So that may require of the order of n, because you have to execute an algorithm to find the max. So 15. So that is the bucket size. So now the bucket size in this case is 15. Now supposing if there is another element whose value is 100, then you need 100 buckets. Okay, that's the drawback. Okay, now what do you do next? So you have to set up 15 buckets now. You can see here. Actually 16 bucket, but 0 to 50. That's the meaning. So this is your B. This is your B. Now start from the first element from the input array A. Pick 10. Now, because it is indexing, right? Because buckets can be indexed. You don't need to search. No searching required. For example, A of 10. Sorry, this one I'll call it as a bucket, bucket array. So B of A of 0 actually. So that is 10. So 10, it should go here. In other words, the 10 will not go here. It is not going to be copied. Instead, assume that initially all buckets have 0. And now go to 10 and make it as 1. From 0, it becomes 1. Okay, next 1, make it as 1. So this is done. This is done. Take 11, go to 11 and make it as 1 from 0. Then 8, make it as 1. Then go to 9, make it as 1. Then go to 15, make it as 1. 12, make it as 1. Then you have 5, make it as 1. Then you have 7, make it as 1. And 4, make it as 1. I think I have ticked everything. Now 0, no element. 2, 3, no. 6, no. 13, 14, no. So they remain as 0. Now what you do, you just collate all these things. How? 1, 4, 5, 7, 8, 9, 10, 11, 12, and 15. So you can see here, it's already ordered. 1, 4, 5, 7, 9, 10, 11, 12, 15. Okay. So that's exactly what the bucket sort is all about. Because we just have picked and indexed, pick the maximum and then indexed it. We need to just make it from 0 to 1 because each bucket can hold only one element. And simply go through this, simply go through this array. Yeah, this one. Whenever there is a 1, just pick the index. Otherwise, just forget it. So when I go to 0, I'm not going to pick that. Because this is 1, so I'll just take 1. Because 2 and 3 0, I don't put it in the output. 4, it is 1, so put it in the output, and so on. So it is simply collating all these ones and their index values will automatically give me the final, sorted array. But what is the drawback? As I said, assume that I have only 3 elements. Okay, one is 5, another one is 170, the next one is 3000. So only 3 elements. Only 3 elements, 5, 170, and how many buckets are required for this? 3000 buckets are required. Because I had to go to first, fifth one, no problem. 117th, rest are all zeros. 117th location and put it as 1. And then go to 3000th location and put it as 1. Which means just for 3 elements, I need a storage because this is the problem with your space complexity. Just for this, you require 3000 buckets. So that's the array size. So that is not logical in the sense, I mean, it's not necessary. So this method fails uh, in terms of the space complexity. Another query or question may be, supposing if I have duplicates, then what happens? Because, for example, assume that I have 8 again somewhere here. Now 8, we have already put a 1, right? Now I have one more 8 coming. So what do I do with this? Okay, so that can be explained using this slide with example 2. Lot of repetitions are there. 4, 1, 2, 3. Yeah, 3 times it has repeated. So it's very simple. You just keep them as counters. So what is the maximum value here? Assume 9. Okay, 0 to 9 is the buckets. So what do I do? 4. So I just make initially 0. Now I'll make it as 1. So when I encounter 4 again, I'll make it as 2. So it's a counter. Third time when it comes, I'll again increment this, right? So it becomes 3. If it appears only one distinct element, no problem. The count will be 1 only maximum. If it is not distinct, then the count value is depending on the number of times that element repeats. So how do I collate all these things? That's very simple. See, from here I have to collate, right? So 0 one time. So sorry, 0 is there. So 0 will not come in the output. Now 1 is actually you have to write 4 times the counter value times. So you can see here 4 times. 2 3 times. 1 sorry 3 one time. You can see 1 time. Now 4 3 times. 3 times. 5 3 times. 0 no. 7 4 times. And 8 2 times. So now it's ordered. So basically, if it's 1 time, you are going to write it in the output as 1 time, but otherwise it's not. Okay, so this is, you know, the case where if you have duplicates, still this method works. Now, the first drawback which I said, it is not solved. Supposing if I have the maximum 3000 and I have just 3 elements, so my bucket size will become 3000 locations. Now, how do I overcome that? So for that, we can actually use what is known as bins. This time, instead of just one element being put in a bucket or bin, we are going to accommodate more elements. So let us assume that we partition this. So this is reducing the number of buckets. So we can partition this like each bin having 10 elements maximum. Okay. So 0 to 9 is one bin, 10 to 19 is another, and so on. So even if I have, so for example, maximum value here is 49, correct? So in the normal case, I need 49 buckets. But in this method, I need just 5 buckets. That's good enough because I have squeezed 10 elements in each bucket. So 50, let's take 50 is the maximum divided by 10. So 5 buckets is enough. So how do I put the values? For example, 29. So it goes into this bucket because 20 to 29. 25, same. 3 will go here. 49 will go here and so on. Some buckets may be empty because no elements are there. So we just toss the elements in an appropriate bucket depending upon the range. Then what do you do? Because you have multiple elements, so you have to sort this. So maybe you can go for, quick sort or heap sort or whatever the sorting, which gives you n log n. Since the number of elements is less, because 10 elements maximum. So obviously time complexity will not be that much problem. So essentially, you have to actually sort this and keep it ready and collate all these things, right? So 3, 9, 21, 25, 29, you can see this is sorted, and 37, 43, 49. Now combine all these things, 3, 9, 21, 25, 29, 37, it is sorted. So the same thing, except that we are saving lot of buckets here from 50 to just 5. 45 buckets are saved, which is drastic. Again, a trade-off has to be done. Now, can I reduce further this? Instead of 10 elements, you can have 15 elements. Yes, that's possible. 3.5 buckets, I think it's good enough. But the problem is you are increasing the number of elements in each bucket. So you have to compromise on that. Keep an eye on how many elements you can have maximum in each bucket. Accordingly, you can have the bucket calculation, right? So this is called as the bucket chart with some variations. Now let us see the algorithm. First pseudocode, then we'll go for the algorithm. So what is the pseudocode for having this? So find the minimum and the maximum, the first step, because given the array A, find the minimum and maximum, divide the interval into n minus 2 buckets of equal length. So this is just to make sure that you know how many buckets you can uh, get depending upon the min and maximum value, because you are just supposed to have the range, you know, calculations. So throw the remaining n minus 2 points into the respective bucket using the floor function. For each bucket that contains more than 1 point, sort them with any method that I told you already, maybe quick sort or heap sort, you can do it. And at most quadratic, that's what. And scan through the buckets and concatenate. So it's only collating the buckets as we have already shown in the previous slide. Now the actual algorithm, because that's only a pseudo code. So now we will talk about the algorithm. So given n elements in A, 0 to n minus 1 is n elements. This is the input array. And what is the output expected? Sorted one. Okay, in the same array is in place sorting. So we'll start with distribution of the elements. Here again, counter, I think, will be there. So duplicates also can be taken care with this algorithm. So we will assume that A is the given array, B is the bucket. So we know that maximum is 15. I just taken this example, but you know that you have to find out, right? Which is the maximum. Accordingly, the size of the bucket you can see here. This is the maximum. So this you have to find out with another sub algorithm, which will get you the maximum element in A. So this is very important. B of A of I. That means A of I will give you the index. So A of I is 0. I is 0. A of 0. A of 0 is 10. Correct? So that is acting as an index. That is B of 10. What is B of 10? Initially 0. Now plus 1. So this will be made as 1 from 0. Supposing if you get one more of the same value, that is 10, then of course you will be incrementing it. That's the idea. So you are going to replace P of A of I, which is 10 in our case, with the incremented value. Next, go for the next element, that is I equal to 1. That is number 1. So what is number 1? That is B of 1. That is this one. B of 1 will be incremented by 1. That is B of 1 is incremented from 0 plus 1 is 1, which will get replaced here. So like this, pick each and every element here and then appropriately put it in the indexed position from 0 to 1 or 1 to 2, whatever. In this case, all are distinct, but even if you have duplicates, no problem. Next, what you should do, you should actually collate, right? So this for loop will do that. And this inner for loop will try to get you the expanded version in case if you have duplicates. So if it's other than 1, that means greater than 1. Supposing assume that 7 has occurred 4 times, so it will be 4. So I need to expand this 4 times. So for that, this for loop will be helpful. So the outer for loop is simply going through this, okay, and putting it back into A. So 0 to max minus 1, that is, we have to run through this array because the size of this is max. So 0 to max minus 1. If b of I not equal to 0 means what? We don't need to bother actually. We just discard it because that element has not occurred in A. So if it's not 0, right, now you have to go through irrespective of whatever be the number here. It could be 1, 2, 3, 4, whatever it is. So that for which I'm using K. 0 to b of I minus 1. That is, supposing if I have ith value here, which means 4 times I have to copy this 7. 7, 7, 7, 7. So K will run from 0 to 3, which is 4 totally, and put that value into A of J, right? Because I have another pointer in order to put that into A. So A of J initialized to 0, starting from first one, you just put that value. Now increment J because you have to copy that to the next element. So this for loop, actually this should be here. So this is the only statement which will be executed under this for loop. So this K up to this maximum value will be copied into this. No, sorry, this is correct. J equals J plus 1 because you have to expand and write in consecutive locations. 4 times you have to write. This is correct. So once you finish this loop, then you will be going to the next position in B and then pick. So this outer for loop will be able to go to that. So inside each of this location, how many ever times you have this, those many times you have to pick those elements, copy that into A, right? And that becomes your sorted, final sorted array that is in A. Okay. Okay. When you come to the analysis part, you will see here that the worst case scenario occurs when all elements are placed in a single bucket. So it's as good as normal sorting, correct? So that's obvious. So which means it could be n square or n log n. But otherwise, assume that the elements are distributed across many buckets, then it depends upon how many buckets. So assuming there are k buckets, so n elements distributed because you have to collect each n elements k times, sorry, k each bucket. So you just have to of the order of n plus of the order of k for every bucket. So this is nothing but of the order of n plus k. So you can just combine these two. So this is the overall complexity. It's good because we are not comparing. So don't think that it has come down. I told you already that only comparison based sorting algorithms, we have found the lower bound concept, but otherwise it's not. Okay. So that's why the lower bound for comparison based is n log n only, but other sorting algorithms like quick sort, sorry, bucket sort, radix sort, there is one more pigeonhole kind of sorting algorithms, etc. So these sorting algorithms may take lesser time, but they'll have additional timing depending upon the number of buckets and other aspects. Okay.